Well, greetings, mathletes, and welcome back. Today we're going to be talking about linear inequalities in two variables. So if we kind of look at the progression we've taken, we solved linear equations in one variable, and then we looked at linear inequalities in one variable, right? That's when you only had x, that was it. Then, now that we've looked at lines and things like that, those are linear equations in two variables. You have an x variable and a y variable. And what the equation does is tells you what the relationship is between the x coordinate and the y coordinate. So basically, if someone hands you an x coordinate, this is what you have to do to find the y coordinate, and now you have your point, right? And we kind of go through things like that. Now, a solution is something that makes the equation true, right? So it's an x and a y value that are tied together into a coordinate, and if I plug in those values, the equation makes a true statement, right? Well, the same is true for inequalities. So let's actually take a look at what one of these looks like here. So if I have a linear inequality in one variable, or in two variables, excuse me, I'm going to go ahead and write this thing, let's say it's this way. Y is greater than or equal to 5x. Now, what this is telling you is that if someone hands you an x coordinate, right? Let's say x equals 2, right? Okay, so that means that my coordinate starts with a 2. If I want to know what things would be solutions for this, well, any y value that is bigger than 5 times this 2 will be a solution. So you actually have choices on how many solutions. It's not like with the lines where you get one and only one point that satisfies this. If I plug in 2 for x, there's a 10 here, but you notice that's y is greater than or equal to 10. So 10 works, but then so does any number greater than 10. So the point 211 works, the point 210.5 works, the point 16,247,822 also works, as long as the y coordinate is bigger than 5 times the x coordinate. It's a solution, right? And so that's basically what this means as a sentence. The y, whatever the y coordinate is greater than or equal to 5 times the x coordinate, right? And that's the relationship between the x and the y coordinate. So we can test this. One of the things you're going to be asked to do in your homework is check to see if something's a solution. So looking at this, let's say, well, we just did that one. Let me just go ahead and pull up another one here. So let's turn that back on, get my blue. So let's look at y is less than 2x plus 1, right? And we want to know if the point 0, 2 is a solution. Now, the point 0, 2, I just totally made it up. I know students always ask me, well, how did you get that? It's not something you get. I just picked a random point because you can do this with any point in the plane, so I'm just picking one. Okay, so let's see if this is a solution. So what we want to do is plug in both the x and the y and see if this comes out to a true statement. So let's see here, y is 2. So 2 is less than 2 times 0 plus 1. Well, let's see here. Well, that's a 0, so I get 2 is less than 1. So that is not a solution, right? 2 is not less than 1. So that point does not work whatsoever. Okay, so let's try another point. Let's see, I have the pen on, yeah. Let's say let's say I have the point 3, negative 1, and we want to know if that's a solution. Well, it's the exact same thing. We're going to plug these things in and just see if it comes out to be true. Plugging these solutions in is actually going to be part of our total solution process in the long run. So this is something that you need to be able to do. So let's see, we're going to check this guy again. So the y is negative 1. let's see, is negative 1 less than 2 times 3 plus 1? That gives me negative 1 is less than 7, and that is true. And so what that means is that 3 negative 1 is a solution, right? And there's an infinite number of solutions to these. There's an infinite number of solutions to equations that are in two variables, but the way the solutions present themselves with an inequality in two variables looks a little bit different. So some of the skills we'll need to be able to do here. One, you have to be able to check to see if something is a solution. That's a necessary skill right now. So you need to be able to do that, and you need to be able to graph a regular line as well. So between those two things, we're going to put those together, and we're going to be able to graph inequalities. Okay, so let's go ahead. I'm going to go ahead and clear this off, and we'll take a look at an example here. All right, let's go ahead and try this one. Let's say we have, oh yeah, that whole turning on the pen thing. Okay, let's try this again. Let's say we have a darker color. Let's say we have a darker color. Oh, forget it. Y is, let's do a greater than or equal to negative 2/3 x plus 1. You know, let's say we need to graph this thing. Well, we are going to need a coordinate grid, and it's the same coordinate grid that we use when, hang on a second here, oops. It's going to be the same coordinate grid we use to graph regular lines as well. So let's go ahead and get that started. Now, the procedure here that we follow when we're, trying to graph lines, we start by graphing it as if it was not an inequality, as if it were a line. And, but my tick marks are getting a little sloppy here, but, well, it wouldn't be the first time, I guess. So let's just get this thing graphed. Okay, so yeah, we actually start by taking a look at y is equal to negative 2/3 x plus 1, right? We go ahead and graph that line as if it's a line. What ends up being the case is that for the inequality, all of the solutions end up being on one side of the line or the other. It's one or the other. So let's see here. Let's go ahead and graph this line first. So we'll go ahead and graph this in blue. So let's see, I have a y-intercept at 1, and then I have a slope of negative 2/3. So that means I count down 2 for the negative 2, and then to the right 3 for the positive 3. And that's how I generate my second point here, right? And so if I went ahead and graphed this, if I went ahead and connected the dots, it would look something like this. Well, that's, well, a little shaky, but reasonably straight. So we end up with our line here, right? Now, it turns out that either all of the solutions are on this side of the line or all of the solutions are on this side of the line. It's one or the other. We don't know which one. So we have to find out. So what we do is you find a point that is definitely, very clearly on one side of the line. Either side. It doesn't matter which side. You just want to pick one. We need a test point. And basically what we're going to do is we're going to pick a point that is not on the line, but clearly on one side of the line. And we're going to plug it in to see if it's a solution. This is why we started with checking to see if something's a solution. So looking here, I have a lot of points I could pick. Any of these would work. So let's see here. Yeah, let's see, like the point 2, 2 would work because that's clearly not on the line. The point negative 2, negative 2 would work. That's clearly not on the line. One of the things I like to do, though, if it's available, because it's not always possible to do this, but you notice the point 0, 0 is not on the line. And we've talked about this before. Zeros are great to plug in because they kill people. They make the arithmetic a lot easier. And a lot of the time, if you're using 0, 0, you can actually figure it out in your head without ever writing anything down, just because you kill so many things. So our test point, this is going to be our test point, is going to be 0, 0. Now, it doesn't have to be that doesn't have to be the test point. I could have used any of the points in the plane as a test point. The only reason I use 0, 0 is because it's convenient. Okay, so if I plug these in, remember that's an x, that's a y. So y is 0 and x is 0. The statement becomes 0 is greater than or equal to negative 2/3 of 0 plus 1. Well, 0 times that goes away, so we have 0 is greater than or equal to 1. That's false. That's absolutely false. This is a false statement. It's a lie. Your math is lying to you if you try to say that this is a true statement. So this comes up false, which means that nothing on this side of the line is a solution. Where all the solutions have to lie are on the other side of the line. So if this came up true, then all the solutions would be on the same side, right? But it didn't. It came up false. So it's always the case that one side of the line is false and one side of the line is true. So if this is the false side, that's the true side, which means that all my solutions lie on the true side. And that's always going to be the case. Whatever side makes it true are your solutions. In fact, that's what solutions are, the values that make it true. And so you end up shading half of the plane, right? It's always on one side of the line or the other. So it's whichever side happens to be true. That's the most important thing. So if you do your test point and you get something true, then that's the side of the line you shade. If you do your test point and you get false, then shade the opposite side of the line. So you always shade the true side. Okay, so that's our first example. Let's go ahead and take a look at a couple more here, because there's actually some notation I didn't explain that we're using anyways. Part of it has to do with this line here too. The only reason this is a solid line is because this has an equal to. Okay, so let's go ahead and take a look at another one here. So let's go ahead and clear that out. And let's try, let's change forms. We did slope-intercept form before. Let's try standard form. So let's say I have 3x plus 4y is less than 12. Okay, so remember the procedure here. We want to graph it as a line. Use a test point to see which side is true. Sorry about my handwriting. Right? So that's the first thing you do. You just graph it like it's a line, whatever it takes. And then once you have the line graphed, you use a test point to see which side is true and which side is false, and then you color the true side. Okay, so those are your steps. So you're going to graph it as a line, use a test point to see which side is true, and then color the side that's true. Okay, so we have this line. We need to graph it, so let's go ahead and start with a grid. Now, being in standard form, the easiest way to go on these is to use the intercepts. So we'll review how to graph using intercepts again. Okay, so first off, if we're going to do this, if we're going to use the intercept method, basically that boils down to choosing good numbers to plug in for x and y to see what your two x and y intercepts are. So if you want to find the y-intercept, you make x 0, right? And that'll be our first point. If I want to find the x-intercept, I make y 0. So those are going to be my 2 points I use to graph this. So if I make x 0, that ends up being 3 times 0 plus 4y equals 12. Oh, not equals 12. Well, we'll do equals because we're graphing the line right now. Okay, so that goes away, and all I really have to do, I really just have 4y equals 12 here, so y is 3. So my x-intercept is at 3. Now, if I want the y-intercept, let's see, that's making y 0. So now this is 3 times x, hang on, 3 times x plus 4y is 12, right? Y is 0 this time, though. Sorry. So that cancels, and you end up with 3x equals 12, so x is 4. And I have my y-intercept now. Now I have 2 points here. I can definitely draw my line, but one of the things I'm going to have a problem with is the fact that when I use a solid line, that means that there's an equal to involved is involved. This doesn't have an equals to, right? There's no equal to here. So we need to denote, that means the line itself isn't part of the solution. All the solutions lie on one side or the other, but not on the line. So to denote that, what we do is we use a dashed line. So you use a solid line when there's an equal to, use a dashed line when there isn't an equal to. It's kind of like using the square and the round bracket, right? Use a square bracket when there's equal to, use a round bracket when there isn't an equal to. It's the same thing. So we have a dashed line now, and now we have to decide which side of this is true. So fortunately for us, the point 0, 0 is available for a test point. Right? So that's what I'm going to use as a test. So if I plug in 0, 0, I have 3 times 0 plus 4 times 0 is less than 12. Well, that makes the computation wonderful. 0 is less than 12. That's true. And that means that this side of the line is true because the test point came out true, which automatically makes the other side false. And your job is to color the side that's true. So this is the side we color. Right? So it ends up being the lower end of that graph. It's kind of interesting how these things end up working out. Okay, so let's go ahead and take a look at another example here. Okay, so you have all the pieces you actually need right now. But let's go ahead and test, see how you do. Let's see if you can graph the solutions to, not y is equal to, y is greater than 2x. In fact, let's throw 2 of them on there. Let's do y is less than or equal to 1/2 x. So we'll throw a fraction in there too. We're getting crazy now. Okay, so go ahead and pause the video here and see what you can do with it. Okay, so I'm assuming you've paused it here. Now, when you graph these things, remember all the techniques for graphing lines are still in play here. So we always start these things by looking at it as if it's an equation, right? Even though it's not, because that's going to be where the boundary is the equation of the line. Okay, so we have y equals 2x. Now, one of the things that isn't written, just because it's extra, is there's always a plus 0 at the end of these things. There's the same thing up here. So if I'm looking at this thing, what that means, if I don't see a number hanging out at the end, then the y-intercept is 0. So my first point is here at 0, 0. Now I'm going to do this a little looser as we graph through this. I'm just going to kind of sketch the graphs. Excuse me. So I have 0, 0, and I have a slope of 2. And remember, all slopes are over 1. So that's 2 over 1, which means I count up 2 and to the right 1 for my second point. Okay, I don't want to draw the line yet. I want to see, is it going to be dotted or dashed? And so I look over here, and there isn't an equal to on here, right? So it's going to be a or dotted or dashed, solid or dashed. So it's going to be a dashed line, right? So I have this to start with. Now what we have to do is figure out which side to color. Now, here we ran into a little problem here. 0, 0 is right on the line. You can't use a point that's on the line as a test point. The line itself is excluded. You need something that's either over here or over here, right? On this side of the line or on this side of the line, one of the two. So we need a test point, something that's clearly not on the line, right? So our line goes here. You could pick anything you want. I'm going to pick the point 1, 0. Notice I'm picking a point on an axis, which means I still get a 0, right? Zeros, it's helpful if you can pick something with a 0 in it. So let's go ahead and do this. So if x is 1 and y is 0, let's see if that's a true statement. So here's our test. Is 0 greater than 2 times 1? Well, 0 is not greater than 2, so that's false, which means that this side is false, and that means this side is true. And if this side is true, then this is the side I color. You always get one true side and one false side, right? So you color the true side. And what it means is if I pick a point on the line, that actually won't be a solution. And because it's not in either half plane, it doesn't tell you which side to color either, right? Because it's not even on a side. You need something that's definitely on a side to know which side to color. Okay, so that's our first one. So let's look at the second one here. Very similar. Difference is the slope is a fraction. So we're going to graph it as a line first, which means that I have this, well, let's do purple. I have a plus 0 hanging out here, which means my y-intercept is at 0. I have a slope of 1/2, which means I count up 1 and to the right 2 for my second point. Now, I need to figure out if it's a solid line or a dashed line. So I look back up here and I see there's an equal to in there, so it's a solid line. Right? Now, it's a matter of picking a point that is definitely not on the line. So what I want to pick, I'm going to pick this one. I'm going to pick the point 0, 1 this time. That's my test point. So x is 0, y is 1. So let's see here. Y is 1 is less than 1/2 times 0. So 1 is less than or equal to 0 is a false statement. That's definitely false. So that means this side is true. And that means that this side is the side we're coloring. And we're going to forgive my coloring skill. I never did well in that section of kindergarten. I don't know why. Anyways. Okay, so hopefully we see that it's still the same process. It's graphing a line and then figuring out which side the inequality makes true, right? That's really what it is. It's the same process every time, no matter what. We can skip some of this process with some of the problems, but and we'll see that here in a minute. But yeah, this is pretty much the process. Okay, so let's try another one here. Let's say we have 2x plus 5y is greater than or equal to 10. Okay, so I want you to graph this inequality. So go ahead and pause your video and see what you can do with it. Remember, graph the line, figure out which side's true. Okay, so go ahead and take off on that. Okay, so let's go ahead and take a look at it here. Now, we need to find the x and y intercepts with this. We're in standard form, and you are certainly welcome to change it into slope-intercept form and all that kind of stuff. The only problem that you may run into when you do that is if this number happens to be negative, that means one of the steps is dividing by a negative, which reverses your inequality, right? So I like to just go straight with the what do you call it, using the intercept method to mess around with this. So that's what we're going to do. We just need some points. So I'll make x0 for one set, and I'll make y0 for the other set. If I make x0, well, you notice really, if I make x0, I'm just kind of ignoring the x, aren't I? If I make x0, that goes away. Oh, that's a 10. And then all I have is 5y equals 10. So you notice if I want to find the y-intercept, I divide by the coefficient of y. So I get y as 2. So there's my first point. And then if I want to find the second point, it's the same thing, except I'm making y0, right? So that boils it down to 2x equals 10, and so x is 5. So my x-intercept is 5. Now I shortened that a little bit, but it's the same, it's pretty much the same process. Well, it's exactly the same process we've been doing. So I have the point 0, 2. There's my first point. And then I have 5, 0. 1, 2, 3, 4, 5. Right? So there's one. There's the other. It has an equal to, so it's a solid line. Right? Okay, now we need to figure out which side's true. Well, 0, 0 is available to us, so we can test this one. So that means 2 times 0 plus 5 times 0 is equal to, or is greater than or equal to 10. Right? Okay, so 0 is greater than or equal to 10. That's false. That means this is true. And that means that we color this side. Right? So it's the top half of this. Okay. So the next examples look different, but they really are pretty much the same thing. What's nice about these is they don't require any computation. It just requires a little bit of critical thinking, and it's pretty straightforward. So let me draw my, well, let's try this again. There we go. Let's draw a graph here. That's a pretty good graph. Well, maybe not that great. Looks better down here on the tablet. Okay, well, let's say, and this threw you off, this threw a lot of you off when we were graphing lines as well. But let's say I have something like x is greater than 3, right? Well, it's still the same thing. You still want to figure out what does the line x equals 3 look like? Well, we already know from the last section that that is a vertical line through 3. Now this doesn't have an equal to on it, so it's a dashed vertical line. Now I know we've been using a test point on this, and you certainly could still, but it's kind of a waste of time. So there's a 3 there. There we go. Here's why. Right? If this line here is where x is equal to 3, the solutions are where x is greater than 3. Well, greater than 3 is this direction, right? That's the direction that things get greater than 3, because that's where 4 is, 5 is, all those things that are greater than 3. So really, when you only have one variable in these things, it just ends up, you just look at the inequality and it actually tells you the direction to shade, right? These are the things that are greater than 3. If I have something like y is less than or equal to 2, Well, we're basing this on the line y equals 2. Well, let's see here. This has an equal to, so it's a solid line. And y equals 2 is basically, I find 2 and I draw a horizontal line through 2. Right? We saw that in the last section. Now, things get greater if I go up. Things get less if I go down. Well, this says less than. So that means that the side that's true is the bottom side. Right? And so these are really, really, really straightforward as far as that goes. There's no computation. It's just a matter of understanding what it says. Because you're just drawing a picture of what it says. That's all you're really doing. Okay. Now, let's go ahead and look at the last case here. And this is kind of interesting because this is where the compound inequalities come in. So you're going to see them show up in two different ways. One of the ways they show up is with x, and one of the ways they show up is with y. And so you handle the x's and y's the same way we did as in the last example. Y makes lines that are vertical, or excuse me, makes lines that are horizontal, and x makes lines that are vertical. So if I have something like this, right? We've graphed these before on a single number line, but if I'm putting it on a coordinate plane, which we are in all of the problems in this section, well, if you remember from the last section when we looked at these, this is a betweenness statement. So this means that y is between -2 and +4, right? Anything between those two values for y will work. Well, -2 is down here, +4 is up here. And if I go ahead and graph it, let's see, at -2 I have the equal to on here. So I'm going to get a horizontal line that's solid here. And then 4 does not have the equal to. So that means 4 gets a dashed line. And remember, this is a betweenness statement. So what that means is the solutions lie between these. These are all the y values that lie between -2 and +4. Right? And so that's the whole graph. You actually get this narrow strip, this horizontal strip. Likewise, if you're dealing with x, I don't know, let's do from 1 up to, we'll just do 5. Okay, so again, these two inequalities here, this less than and this less than or equal to, they could be anything. I'm just picking things randomly. They might both be less than or equal to, they might both be less than, or they might be mixed, as we've seen. So you just need to, mark the graph accordingly. So let's go ahead and make our graph here. Now this is x, so that means I'm going from 1 on the x-axis to 5 on the x-axis. At 1, I don't have an equal to, so it's a dotted line or dashed line. At 5, I do have an equal to, so it's a solid line. And anytime you see these triple inequalities like this, that's a betweenness statement, so it's everything in between. Excuse me. Right, so you can see, if you look just at the axis itself, right, I could actually go ahead, let me switch colors so it stands out. Maybe green will stand out. If I actually went ahead and made the interval on here, it would look like this, right? I'd have a round bracket on one side, a square bracket on the other, right? And these things correspond. The solid line corresponds with the square bracket. The dotted line corresponds with the round bracket. So there's definitely a connection here. Okay, so clear that off. Okay, so that was the last of the stuff I needed to cover today. So, in any case, we'll be continuing on next week. And until then, keep your pencils and your wits sharp.